Hi, welcome to the fourth program of Microcontroller and Embedded System Laboratory. Let us start understanding what are data reservation directives. The data reservation directives are DCD, stands for Defined Constant Data. This allocates one or more half words of memory aligned on 4-byte boundaries. DCW, Defined Constant Word, allocates one or more half words of memory aligned on 2-byte boundaries, and DCB to define constant of byte size. Among the different data processing instruction, the next data processing instruction that we have to understand for this program is logical. Logical instructions, as usual, we are going to have instruction conditions, S prefix to indicate that we are interested in to look at the CPSR flags, then destination registers and the operands. The logical instructions are AND, OR, exclusive OR and bit logical clear instruction. Among these instructions, we will understand what is AND instruction mean. AND is a logical instruction on which AND operations are done on two operands and the result gets stored in the RD registers. We use AND instruction whenever we are interested in masking the bits. When S prefixed with the AND instruction, it is going to affect N, Z and C flag, that is negative, 0 and the carry flag. Now let's look at the example. When R1 is having the values as 4456 followed with 4 threes, and the second register which is used for masking the first value, we refer R2 is equal to zeros followed with F. When done an AND operation on this, the destination register R0 will contain 0000 and 3333. So in this way we can mask the bits and we can get what the values we are interested in. The next is addressing modes. Now this addressing modes is going to specify at what point are we going to have our offset to be applied. If we apply offset before transfer is made, it is called as pre-index addressing. Optionally, auto-incrementing the base register by post-fixing the instruction with an exclamatory will be called as auto-index addressing. The other one is when the offset is applied after transfer is made is called as post-index addressing, causing the base register to be auto-incremented. The program is write the program to add an array of 16-bit numbers and store 32-bit result in the internal RAM. Now that means we are going to have an array of 6 numbers which are given with the data reservation directives are DCW, indicating that we are allocating one or more half words of the word align to be in 2-byte boundary is the DCW. These are the numbers which are 16-bit and it's an array given with the name as value 1. We are going to have the result to be stored. That result is labeled with the DCD, that is defined constant data, with the name label as result. We are also declaring one more called as DCD, which is defined constant data, which contains for masking the value on the register. Since all our registers are 32-bit and we want only to get the 16-bit, we are going to use a variable called as mask, and this is the value that the mask is going to contain. Now we are trying to add 6 numbers. So R5 is a counter which contains the value as 6. R0 contains the result of the summation. So R0 is initialized to 0. We have our LDR where R1 is going to contain the address of the first number value 1. We have LDR R2 comma, and this is an example of post-index addressing. First, the address content which value 1 is being there, the first number will be shifted to R2 and then it gets incremented. As the value we have is DCW, which talks about 2-byte boundary, so we are going to specify that #2. That means we have 2-byte boundary, and after transferring the value to my R2 register, we are incrementing this by 2 offset value. R3 is loaded with the mask value, that is 0000FFFF is what is there in R3. We do AND operation. When doing the AND operation, any number which are the 4 bits will not be there, and we just retain with the 16-bit number, and that will be moved to your R2 register. Then we do the AND operation. After doing the add operation, the first number that we have with R0 is 0. So it adds 0 with 1, 1, 1, 1, and the result is stored in R0. Since we have finished taking the first number and added, so we are reducing R5 by 1, which is a counter for us. We compare whether R5 is equal to 0. No, R5 has reduced to 5. That means, which indicates there are 5 more numbers to be added. And that means branch not equal to loop. It goes back to the loop. Again, the second number is moved to R2 and it is incremented by 2. 2 is the offset. Again, we mask the second number. Take that number, add it with the first number, and then we decrement the value, and this loop continues till R5 becomes 0. Once R5 becomes 0, it comes to the next instruction where the result is moved to R4. That means R4 contains the address of the result variable. Then we are going to store the contents of R0, with that is the sum value is moved to the location where R2 is pointing to. This is a convenient way of stopping the program, and here we end the program. Let us trace this program, which is going to talk about addition of an array of 16-bit number and storing the result in a 32-bit result in an internal RAM. So as we discussed earlier, we have area, the name, code is read only, and we have a set of machine instruction. Now I'll not go more in detail because we are already in the 4th program. So I directly go to the iterations by saying that R5 is a counter which gets decremented at every time when it makes a comparison here. Then we initialize R5 to 6, R0 is set to 0. The first R1 is going to contain the address of the first number, which is a value 1. So we are going to have the address in R1 for the first time. Then we have LDR R2 with this instruction being executed. It goes to the address where we have the number, and it is going to store 32-bit value which moved to the register R2, and then R1 gets incremented. So we have this 32-bit number stored in R2. R3 is being moved with the mask value. On doing the AND operation, R2 retains the 16-bit number that we have stored here. So it will be retaining only the actual 16-bit number that we want. It adds this value with R0, and again R0 contains the result of the summation. Then R5 gets decremented. Since R5 is not equal to 0, it goes back to the loop. Then the next number is there in this particular address. It takes that number and then adds 0 to, and then R1 gets the new value, something like this. Again, it masks the value to get the only 16-bit number. Add that number with R0. Again, R0 contains the result of the summation of the first number with the second number. Like this, the iteration goes on till the R5 becomes 0. When R5 becomes 0, 0 flag is set and then comes out of the loop. The next instruction after loop is loading the address of where my result has to be stored to my register R4. So for example, R4 contains the value of this number, which is the address of the result. We are going to move the answer which is there in R0 into the location of 0x4 followed with 7 zeros here. It is moved, and stop B stop is an infinite loop, which is a convenient way of stopping the program, and then we come to the end of the program. We will see how the program gets executed in the next part. Thank you.